Okay, welcome back from the weekend. Welcome back to winter, and we've got to get going today. There's an announcement in here about a pre-medical honor society meeting if you're interested, so that'll be this week, Thursday. Details will be posted in the notes. One other announcement before I start is that there will be a slight change to office hours tomorrow, or at least the time that I'll normally be there. So tomorrow, which is Tuesday, I had a meeting get scheduled from 11 to 12, so I'll be actually available 12 to 1, so 1 hour later. If that time doesn't work, then I do have some other availability throughout the day. You're welcome to schedule with me anytime. All right, so that's the one announcement I have. And what we're going to do today is we're going to continue on with, we're actually going to finish Chapter 5, which is Stoichiometry, a big topic for us. That's going to continue to come up in later chapters as well. And just to orient you on where you are, on where we are, remember that our second exam is chapters 4, 5, and 6. We have spring break next week, and then 1 week after getting back is when the second exam starts. So it's all going to come pretty quickly. So now is not the time to zone out and start thinking about spring break. We still have a whole week before that. All right. So what we're going to do today is following up on what we ended with last time. So if you were here last time in a somewhat conscious state, you would have seen me go through this slide. It takes an uncomfortable long amount of time for people to chill out and stop talking, so can we fix that, please? All right, thank you. All right, so the process for stoichiometry we kind of outlined in abstract last time. We said that we've done all kinds of conversions involving mass and moles already, and now we're going to combine that with using a balanced chemical equation and stoichiometric coefficients in the chemical equations to link the amount of one substance to the amount of another, the key link being the mole ratios, the moles of one substance related to the moles of another that also participate in the same chemical reaction. And then using those moles, we can go back and calculate mass or whatever other relationships we'll have in the future that involve moles. So that's kind of the process. The best way to learn the process is to do it over and over again, just like most things in chemistry. So let's see a few examples of this in practice. All right, so we have this reaction here. If you're curious, this is gold plus nitric acid plus hydrochloric acid. The mixture of nitric acid and hydrochloric acid is called aqua regia, water of kings, because it's one of the only substances that can actually dissolve gold. Fun little trivia for you before we get started. And it forms these products. So anytime we do a stoichiometry problem, we have to have a balanced chemical equation before we start. Here it's given to us. Sometimes that will be the case, so we don't have to necessarily produce or balance a chemical equation. It's already there for us. But then we have to dive right in and see what the question is asking. It wants to know how many molecules of water are formed when 2.56 grams of gold is completely converted to the product HAUCl4. All right, so these types of problems I'll set up pretty much the same way I do any other type of conversion factor type approach, which is just to start with what we're looking for. So very often these problems have a lot of given information. A lot of times occasionally they will have extraneous information that you don't actually need, but what I like to do is always go to the very end of the question, look for what it's actually asking you to do, because that'll help you figure out what steps you're going to likely need. So we're looking for how many molecules of water are formed. So we should think that we're going to use Avogadro's number at some point because we're looking for the total number of either atoms or molecules or whatever. So that's going to be involved. But we're starting with 2.56 grams of gold. So again, in stoichiometry, you're going to be relating two or more different substances to one another. So we start with a different substance, gold. And then, my mantra in stoichiometry, which I'll say over and over again, and I've already said it to some people that have come to my office hours recently, is when in doubt, convert to moles. So you're given a mass amount of one of your reactants in this case. If you don't know what else to do, at least start out by converting it to moles. And typically speaking, in a stoichiometry problem, that is going to be the first thing you want. You want to get moles of whatever reactant or product you're talking about. So to convert to moles of gold, just the same step we've done millions of times now, which is to use the atomic mass. So 1 mole of gold, we divide by the atomic mass, which from the periodic table would be 196.97. So grams cancels out, that gives us moles. But what we're interested in as we look back is molecules of water, not molecules of gold or atoms of gold. So we have to then use stoichiometric ratios to link one to the other. All right, so again, once we have moles of one substance, we can always figure out how many moles of another substance will either be formed or will react along with it, and we use the mole ratios for that. So we want moles of gold to cancel out and take us into moles of H2O, and we just have to look at the coefficients in the chemical equation. So water has a coefficient of 2 in front of it, so there's going to be 2 moles of water for every, and there's no coefficient in front of gold, so it's going to be per 1 mole of gold. Remember, anything that doesn't have a coefficient, the coefficient is actually 1. So this allows us to then figure out how many moles of water will be formed when this much gold reacts. But then what we're looking for is molecules of water, and so that's, again, that last step here, which is going to be Avogadro's number. 6.02 times 10 to the 23rd water molecules in 1 mole of water. Remember, Avogadro's number tells us how many of the smallest building blocks are there in 1 mole of substance. So for water, water is made up of molecules, so there's going to be Avogadro's number molecules in 1 mole. And that cancels out moles and gets us to what we're looking for. So when you set up the problem this way, as soon as what you're looking for matches the units that are left, and you're at your last step, and you can stop there. Okay? So we stop there, we calculate out the number, and we get 1.56 times 10 to the 22nd molecules. Okay? All right, and obviously in Blackboard, if it was a numerical question, you'd either enter the number or the log of it or something. Okay, but those are the series of steps. The key new one for us is this one here, the stoichiometric ratios that allow us to convert an amount of one substance into an amount of another. Everything else is just the same types of calculations we've already done. Avogadro's number, molar masses, things like that. Okay, any questions on that one? All right, we'll do one other example that's a little bit more involved, at least gives us more of the steps. All right, so in this problem, we're talking about a different oxide of iron. We talked about rust a little bit last time, but another oxide of iron is called magnetite. It is magnetic, as the name would suggest. And you can make magnetite, and one way to make it anyway, is to take iron metal, react it with water, and it will form Fe3O4 and release hydrogen gas. So the question is asking us how many grams of water are required to react completely with 25 grams of iron. So in other words, if we're putting in 25 grams of Fe, how much water do we have to put in along with it to get that to completely convert to the products? The issue here, though, is unlike the last problem, we don't have a balanced chemical equation given to us. So there are going to be times when you're going to have to use the information in the problem, potentially some knowledge of nomenclature and things to be able to pull out what the chemical equation is that we're talking about. All right, so we're looking for keywords here. So we have iron reacts with water, so that would suggest that those are our two reactants. Iron is just Fe. Water we should hopefully know is H2O. And then we're going to have products, which is going to be this Fe3O4 to form. So whenever you say it forms something, those are going to be the products. Fe3O4 and hydrogen gas. All right, I should leave a little bit of space where we might have to add some coefficients here and there. Okay, so those are the reactants and products. And then we're going to follow the same steps that we did last time for balancing. I would suggest setting this as a coefficient of 1 because it has the most atoms in it, and then we can balance everything else relative to that. So we fix that to 1. We have 3 irons on this, Fe3, so we need to put a coefficient of 3 there to make sure we have 3 irons on each side. The next one, we can do either hydrogen or oxygen, I suppose. But let's do oxygen first because we have 4 oxygens here. That means we need to have 4 waters to make sure we have 4 oxygens on both sides. And then we'll do hydrogen last, because now that we know that there's 4 oxygens, that gives us 4 times 2, which is 8 hydrogens, which means we need 4 H2s. So that would be how we could balance that equation. We can check ourselves, as always, to make sure. So on each side of the equation, reactants and products, we should have the same number of each element. We have 3 elements involved in this, iron, hydrogen, and oxygen in different forms. On the reactant side, we have 3 times 1, which is 3 irons. On the product side, we have 1 FeO3, which has 3, so 1 times 3 is also 3, so that checks out. Hydrogen, we have 4 waters, so we have 4, each water has 2, so that's a total of 8 hydrogens on the reactant side. We have 4 H2 molecules, also 4 times 2, or 8 on the product side, so we have the same number of hydrogen on both sides. And then for oxygen, we have 4 waters. Each water has 1 oxygen, so that's 4 oxygens. We have 1 Fe3O4. You don't necessarily have to do this step, as I said, but if you have time and are paranoid about your ability to balance chemical equations, it's always good to do this. So we make sure that the reactants and product side both have the same number and same types of each element, and we're good to go. So we have the correct coefficients. We're going to need those to use later on. So if you don't have the balanced chemical equation, we talked about that topic last time, so it's something we've already handled a little bit in class and on the homework assignments, but make sure you're able to do that effectively. So once we have the balanced chemical equation, which I will write out once again so we have it right in front of us, that's the balanced equation we just came up with the correct coefficients, correct reactants and products. Then we can go ahead and do the calculation like we did before. This time it's going to be a more common one, which is mass to mass. So we're given a mass of one of our reactants, iron, and we want to know the mass in grams of water that reacts with that. So this is a more practical way, at least, of doing stoichiometry. We don't usually need to know how many molecules are involved like we did last time. So we're looking for the grams of water. And so again, we're going to write out what we're looking for, and we're going to start with what we're given, which is going to be 25 grams of iron. And then we just have to go through and figure out how to make this conversion. So the first step is going to be always to convert to moles if we're not already in moles. So 1 mole of iron has an atomic mass, if we go to the periodic table, of 55.85. So we divide by that to get moles of iron. At this stage, we can then convert into moles of water. We're looking for water, so we want to make sure we can figure out how much water is involved as soon as possible. This is the stage where we can do that. We look at the balanced chemical equation. So again, we want moles of iron in the denominator. We want moles of water in the numerator, so that moles of iron cancels out, and that gets us into water. We just look at the coefficients. 4 moles of water, coefficient of 4, per every 3 moles of iron with a coefficient of 3. So that gives us moles of water, and again, depending on what the question was asking, we could stop here, but the question is asking for grams of water, so we want a mass amount. We have the molar mass given to us here. So we have to do one last step, which is to multiply by the molar mass. So moles of water in the denominator, grams of water in the numerator, that's going to be related by molar mass, which is 18.02 grams per 1 mole. So now moles of water cancel out. That gets us into grams, which is what we're looking for. So again, when the two match up, that means you've done all the steps you need to get there. And what this comes out to is 10.8 grams of water. All right. So that tells us if we have 25 grams of iron and we want to convert it completely into Fe3O4 magnetite, we need to also include 10.8 grams of water for that to happen. All right. Any questions on these couple of problems? All right, so those are sort of the basics of stoichiometry, 2 typical types of problems that involve just calculating amounts of reactants and products, but we do have to consider something else that can happen sometimes as well. So in this problem, we figured out that we had 25 grams of iron, we needed exactly 10.8 grams of water for this reaction to go, but what if we had mixed those together in different ratios? What if we had 25 grams of iron and we added instead 8 grams of water, or we added, a lot of extra water, like 100 grams? We have to figure out which one of those reactants is going to determine the amount of product that can form. Now, perhaps an easy analogy to this concept of limiting reactant would be like a cooking analogy. So imagine that you want to bake, let's say you have, let's say you want to bake 20, I don't know anything about baking, so I hope my analogy is not awful, but let's say you want to bake 24 cupcakes, and the major ingredients are going to be flour, eggs, and sugar, okay, other things obviously as well. So if you want to bake 24 cupcakes, let's say you have, plenty of flour and plenty of sugar to do that, but you only have enough eggs to make 12 cupcakes. Well, how many cupcakes can you actually make is just 12, right? So in that case, one of your ingredients limits how much of the product you can actually form. And the same thing is sometimes true in chemistry. If we take 2 reactants or 2 or more reactants and mix them together, and we don't have them in exactly the right ratio, one of those is going to end up limiting how much of the product can form, and that's what's called the limiting reactant. So we have to, in many cases, determine what the limiting reactant is. It wasn't an issue in the problems we've done so far, but we'll see that it does come up from time to time, and we'll explain when this is an issue as we go through this. All right, so limiting reactant is the situation where one of your reactants is going to determine how much product can actually form. So there's 2 ways of doing this, and I encourage you to use whichever way you're more comfortable with. If you follow along closely with the book, they have a method that that works. It's not my favorite method, but it works. It's not too difficult either, I don't think. So the way you do it is really for any type of limiting reactant problems, any stoichiometry problem where we have two or more reactants, we want to figure out which one is going to limit the amount of product that forms. We have to determine the moles of each reactant. And for argument's sake, I'll call these reactants A and B. They could be any two things that are reactants in the chemical equation. Remember, a limiting reactant, as the name implies, is always a reactant, always something on the left side of the arrow. You're never going to have a limiting product or anything on the right side. All right, so we have that situation. We determine the moles of each. And then what you do is you do sort of a hypothetical calculation. So we say, well, okay, let's determine how many moles of B are required to react with that many moles of A. So you're going to do basically a stoichiometry calculation. Using mole ratios like we would before. All right, so you take the amount of one reactant in moles. You figure out, okay, if I have that many moles of one reactant A, how many moles of the other reactant B would I actually need to react with that? And then you compare the two numbers, the amount that you calculated and the amount that's actually there that you determined in the first step. So if the amount that you calculate is less, and this is where I think this approach gets a little bit confusing because you have to keep these two scenarios straight in your head, and sometimes they're not easy to remember which is which, or if it's not, it's not always intuitive, I guess, or depends on how you think about this. But anyway, if the amount you calculate is less than the actual amount of B, that's there. So again, you have two numbers, the amount that's actually present, which you got in the first step, the amount that would be required, which you calculate in the second step using mole ratios. If the amount that you calculate is less than the actual amount present, then that means A is the limiting reactant. In other words, you have more than enough B to react with however much A you have. And then you'd have the opposite situation, which I'll just write as vice versa. So if you calculate an amount of B that is greater than the amount that you actually have, that would make B the limiting reactant. Now, like I said, sometimes it's hard to keep those situations straight. I think it does make sense logically. If you calculate an amount of B that's too small, that means you have more B than you need, which means A is the limiting reactant. If you calculate an amount of B that's less than what you actually have, that's greater than what you actually have, that means that you need more B, so that means B is what's actually limiting you. Hard to keep straight sometimes, so there is a way that I prefer to do this, which is not, I call it the sort of short way. It's not really shorter than this, I would say. But the nice way about doing it this way is you just have to compare two numbers and not think about, is it bigger or smaller than, what does that mean, all that stuff. It's just you look at the number, the smaller one isn't immediately the limiting reactant, you're done. There's one caution of the step that I'll point out later. But what we're going to do in the way that I was taught, again, more years ago than I care to admit at this point, when I was taking this same class or the same version at my university, the way that I was taught to do this, which I've really liked over the years, is to determine what's called the stoichiometric ratio for each reactant. All right, so I'm going to abbreviate this with capital R. And what it's defined as is just like before, we calculate the moles of each reactant. So that step we have to still do. And then all we do is we divide this by the reaction coefficient. So of course we're starting with a balanced chemical equation where each reactant is going to have a coefficient in front of it. And if you take the number of moles of that reactant that you have and divide it by the reaction coefficient, you get what's called a stoichiometric ratio, which I'll abbreviate as R. And then all I have to do is say that the reactant with the smallest stoichiometric ratio R is going to be the one that's the limiting reactant. So I think it's a little bit easier to keep that straight than the other scenario that I gave you before. All right, so whichever one has the smallest stoichiometric ratio will be the one that's the limiting reactant. And I'll abbreviate limiting reactant very often as LR, so we're familiar with that. All right, so I think this is a slightly easier approach. It's not necessarily a shorter approach, but then you just have to compare two numbers and pick the smaller one and identify that automatically as your limiting reactant. Now, the caution of this approach, which I'm going to warn you guys about now and see how many of you heed this warning in the future, is that this stoichiometric ratio R, it's great for determining what the limiting reactant is, but then as soon as you have that, it's useless after that, okay? So don't try to use R for anything else except for determining what the limiting reactant is. Okay, once you know what the limiting reactant is, your subsequent calculations are always going to not going to start with that value R. They're going to start with the moles of that reagent. All right, we're still alive. All right, so all subsequent stoichiometric calculations, so whether you're calculating amounts of products that form or amounts of other reactants that are consumed in the reaction, all of these are going to start with the limiting reactant. So that's really the value of determining limiting reactant. So we don't want to use stoichiometric ratio R anymore after this. Once we know what the limiting reactant is, we're going to use that amount of limiting reactant to calculate anything else we want to calculate, which is amount of product that's formed or amount of other reactants that are consumed. So the limiting reactant determines everything about that chemical reaction in terms of reactants consumed, products formed. All right, but don't use R for anything else but helping you figure out what the limiting reactant is. All right, so you do need to know what the limiting reactant is, because if you start with the wrong reactant in these problems, you're going to calculate the wrong amount of substances. But once you know what it is, we don't want to use that number for anything else. Okay, it's a ratio, so it's not a very useful quantity on its own, except for determining what the limiting reactant is. All right, so let's see how this works then, because again, examples are key. But before we see how it works, let's answer the question that's likely burning a hole in your minds right now, which is, how do I know if I even need to do this? Because we've done a few stoichiometry problems already in class today. We didn't have to even worry about limiting reactant. We just started the problem. No big deal, right? And so the way we know if you have to calculate limiting reactant or determine limiting reactant is if you are given amounts of two or more substances, two or more reactants specifically. So if we know how much reactants we have for more than one of them, so if you're given amounts of two, or in rare cases more than two of the substances that are reactants, you have, I don't like to use absolutes, but this is one where I feel comfortable, you must first determine what the limiting reactant is. Okay? I remember amounts could be, we have the mass of two reactants, or we have the moles of two reactants, or we have the mass of one reactant and the moles of the other. If you know something specific about the amount of two or more reactants, a precise quantity of that reactant, you need to be able to figure out which of those two is limiting reactant. If we only tell you the amount of one of the reactants and say that the other one is in excess, or we don't really specify, if you only have the amounts of one reactant, then you don't have to worry about it. You just assume that that reactant is limited. So if you are given an amount of only one reactant, so there are going to be some of the simpler problems like we did earlier where you just know the amounts of one reactant, like the last one we did with iron and water. We didn't tell you anything about the amount of other things. So if you're given an amount for one reactant and only, and don't know the amount of the other, we can just start the problem. Or additionally, we sometimes have problems where, the starting point in the problem is going to be an amount of product. So if we're setting up a question where we say, you want to form this much product, how much reactant do you need? Well, in that case, you don't have to worry about limiting reactant either, because we're starting with an amount of product. But in a case where we give you amounts of two reactants, that's when you have to determine a limiting reactant. But if that's not the situation, if we only give you the amount for one reactant, or we're starting with a product amount at the beginning of our calculation, we can just start the problem as normal. Just start the calculation like we normally would. Don't have to do the extra step of determining a limiting reactant. All right? So I do often find that one of the more difficult things for students to grasp in this section is, when do I have to even go through the steps to find the limiting reactant? And it's really any time you're given amounts of two or more than two of the reactants in the problem. All right, so let's see how this works then. We'll do one example together, or a couple examples, I guess. So here we're again given the balanced chemical equation, ammonia plus fluorine making N2F4 and hydrogen fluoride. We want to know how many grams of this product N2F4 can be obtained if we have 5 grams of ammonia with 15 grams of F2, 5 grams of NH3, 15.0 grams of F2. All right, so again, this is a clear situation where we have to figure out which one of those is a limiting reactant because we're combining two reactants. We have the amounts of both, 5 grams, 15 grams. We need to know which one of those is going to limit the amount of product formed. Those aren't necessarily the exact right ratios of those two reactants. So the first step is to determine the moles of each reactant. So when we have grams of both reactants, we determine the moles of each one. And that's going to be just using molar masses like we've always done. So the moles of NH3, at this point we don't worry about anything with stoichiometric coefficients yet. We're just going to calculate moles like we normally would. So we have 5 grams of ammonia. We divide that by the molar mass, which is 17. All right, so same mass to mole conversion. We get 0.294 moles of NH3. And then we're going to do the same thing for the other reactant. F2, we're going to take 15 grams of F2 and convert that to moles using its molar mass, which is going to be given to us here. Remember, the script capital M means molar mass in this context. All right, so 1 mole is 38 grams. We divide those two, and we get 0.395 moles of F2. Now, another common mistake that people make is they say, oh, I have less moles of NH3, that must be the limiting reactant. But remember, that's not alone enough to tell you that. We have to divide the moles by the stoichiometric coefficients to figure out which one the limiting reactant is. Because in the balanced chemical equation, they participate in different amounts. 2 moles of NH3, 5 moles of F2, that ratio. So to get the stoichiometric ratio, then we have to divide by the coefficients. So we're going to determine stoichiometric ratios for each of these. That's the second step. The nice thing is, at least for one of the two, calculating the number of moles is not a useless quantity. So it's not like we're going to necessarily throw these numbers away when we're done. We're going to use one of them. But we have to determine stoichiometric ratios first to identify limiting reactants. So we do it for NH3 first. We take the moles of NH3 and divide it by the coefficient, which is 2. So 0.294 was the number of moles. 2 is the coefficient up here in the balanced equation. And we get 0.147. And we do the same thing for fluorine F2. The number of moles for fluorine we determined was 0.395. And we divide that by its coefficient, which is a 5 in the balanced chemical equation. And we get 0.0790. And then the smaller of those two is going to be the one that's the limiting reactant. And it's very obviously going to be this one here, which is smaller of the two stoichiometric ratios. So we've identified with this series of steps that F2 is our limiting reactant. And we notice the importance of doing these steps because we see that fluorine, we have a larger mass, 15 grams versus 5 grams. Fluorine, we also have more moles, 0.395 versus 0.294. Yet in spite of being greater in both of those respects, it has the smaller stoichiometric ratio, so that's going to be the one that's our limiting reactant. So can't skip any of these steps if we're going to do it this way. All right, so F2 is our limiting reactant. So once we determine that, we then go through and start the calculation. And our calculation has to start with limiting reactant. So our third step here is going to be to do whatever calculation we need to do for this problem. And we're going to start with our limiting reactant F2. So at this point, the amount that we have of our other reactant, NH3, doesn't matter anymore. We just have to start with our F2. And what we're looking for here is how many grams of N2F4 can be formed. So grams of N2F4, we can go back and use the moles that we can either start with the mass of F2, which is 15, or remember the first step is going to be to convert to moles, so we can just start directly with this number here that we already calculated. Either way will get you there, but one less step if we just start with number of moles of F2, which we already calculated. But that's our limiting reactant, so we have to start with that one. And then we just use coefficients to figure out moles of our product N2F4. So moles of F2 to cancel out in the denominator, moles of N2F4, which is what we're looking for. This has a coefficient of 1. F2, as we saw, has a coefficient of 5. And then we want to find the mass of our products. We're going to use its molar mass, just like we did in the last problem, to calculate a mass. So 104.0 is the molar mass. So it's going to be 104.0 grams of N2F4 in 1 mole of N2F4. Moles cancel out. That gives us grams of our product, which is 8.22 grams. All right, so if you had started with instead the amount of NH3, you would have calculated a number larger than that, which would have been not the correct amount. So again, the F2 has a limiting reactant. It's going to limit how much our product of our product can form, which ends up being 8.22 grams in this case. All right, so any questions on the concept of limiting reactant or how to use it in a stoichiometry problem? All right, the last thing that you'll sometimes be asked to do then is we want to know how many grams of excess reactant remain. So whatever is not our limiting reactant is going to be what's called our excess reactant, the one that has more amount than we need, or what that is in excess, as the name implies. So if F2 is our limiting reactant, that means the other reactant, NH3, is our excess reactant. And we want to figure out, when the chemical reaction is done, how much of that is left over. So if it's our excess reactant, there's going to be some amount that doesn't participate. And we're going to figure out what that is. So the first thing we're going to do is we're going to figure out the grams of ammonia that are actually consumed. So if all of our limiting reactant reacts with NH3, how much of the NH3 actually is going to be reacting with it? So again, start with the moles of limiting reactant, which was 0.395 moles. And then we're going to calculate the amount of NH3 that reacts if we have 0.395 moles of F2. So we again use stoichiometric ratios here. 2 moles of NH3 are going to react for every 5 moles of F2. That's what those numbers tell us. So it's 2 moles of NH3 for every 5 moles of F2. And that gives us moles of NH3 that react. And then if we want to convert that to the amount in grams, we use the molar mass of NH3, which was given to us earlier as 17. So there's 17 grams of NH3 in 1 mole. All right? So this allows us to figure out if all of our limiting reactant F2 reacts with NH3, how much NH3 is that actually going to be? And that comes out to 2.69 grams. And remember, that's the amount of NH3 that was consumed in the reaction. That number directly is not the amount that's left over. That's the amount that actually reacted. And then to find the excess NH3, we just subtract from the original amount. So we were told at the beginning of this problem that we were putting in 5 grams of ammonia. We determined that this was the excess reactant, so that's more than we needed. So 5 grams was our starting amount. And then we're going to subtract the amount that was consumed, which you just calculated, 2.69 grams. So that's the amount that's consumed, and that means that we have 2.31 grams left over. So if we're ever asked to determine how much excess reactant is remaining after the reaction is over, you have to do a sort of a by difference. You know how much excess reactant you started with. That's going to be given to you in the problem. We use stoichiometry to figure out how much of our excess reactant is actually consumed and converted into our products. And then the last step is to subtract the two to figure out what's the actual amount remaining. Okay, any questions on that? All right, let's do one other one, just to get the hang of this. All right, so we have another reaction involving ammonia, which is N2O plus sodium going to NaN3, NaOH, and N2. This compound here, in case you're curious, is called sodium azide. It's used in airbags, so if you give it a shock, it reacts explosively to make nitrogen gas, and that's what blows up your airbag. So that is a real compound that's used in well, hopefully not in our everyday lives, but it's important. All right, so we have to figure out, in this problem, first we have to figure out what is the limiting reactant. So again, we're going to take you through step by step. We have the balanced equation, and we're telling you that we have 5.25 grams of N2O, 4.05 grams of sodium, and 2.57 grams of NH3. So I'm going to be even worse to you here and give you amounts of 3 reactants. So in this case, we have to calculate the moles of all 3 reactants and the stoichiometric ratios for all 3. Whichever one of those 3 is the smallest will be the one that's limiting reactant. So same series of steps, but just one additional time. So for each reactant, we're going to calculate moles. So N2O, we have 5.25 grams. And we use this molar mass to find moles of N2O, which is molar mass is 44.01. That's 0.119 moles, and then the stoichiometric ratio is going to be that number divided by its coefficient. So N2O has a coefficient of 3, so we're going to divide this number by 3, which is 0.040. We don't need too many significant figures here. So that's the stoichiometric ratio for N2O. Wait till my tablet comes back to life. Let's continue. Hopefully it will. Alright, there we go. Alright, we're going to do the same thing for the other 2 reactants. So next one is sodium, Na. We just use the atomic mass of sodium, which I was kind enough to give you in the problem, so you didn't have to look it up. So it's 4.05 grams of sodium. We use the atomic mass, which is 22.99, to find out moles of sodium. All right, so that comes out to 0.176. And then its stoichiometric ratio is that number, 0.176. Divided by the coefficient for sodium, which is 4. So we get a number that's actually fairly similar, but a little bit bigger, 0.044 in this case. So it's a little bit larger, so that means that sodium is not going to be a limiting reactant. And then we check the last one, which is NH3. We have 2.57 grams. We calculate moles using the molar mass of NH3, which is 17. So we got 0.151 moles. And then its stoichiometric ratio is 0.151 divided by the coefficient, which is just a 1. There is no coefficient in front of NH3, so that comes out to 0.151. So the smallest of these 3 numbers, the stoichiometric ratio, is 0.040, 0.044, 0.0151. This one wins or loses by a hair, depending on what your concept of winning and losing is, but that's our limiting reactant either way. All right, so we identify this one as our limiting reactant. We had to do the same series of steps for all 3. We picked the smallest one as our limiting reactant. So that's going to be N2O. So that'd be the answer for this one is A. Now, in most cases, we're not going to ask you to just identify the limiting reactant. We're going to ask you to do some calculation with it. So if we want to figure out how much of our sodium azide, NaN3, can be theoretically obtained in this reaction. So we always have to then start with our limiting reactant, which we identify was N2O. So even if we had not explicitly asked you to identify the limiting reactant as a separate question, we would have had to still do that anyway to figure out where we start this calculation. So we're going to start with N2O and look for the grams of NaN3 that form when that much N2O reacts. So as we determined in the previous step, there are 0.119 moles of our limiting reactant. We can use that as our starting point instead of undoing that step and starting with mass again. So we have 0.119 moles of N2O. And then we use stoichiometric ratios to figure out how much of our product can form. So moles of NaN3, moles of N2O in the denominator to cancel out. Our product has a coefficient of 1. Our limiting reactant has a coefficient of 3, so it's going to be a 1 to 3 mole ratio. And then we use molar mass of NaN3, 65.01 grams. To convert moles of NaN3 into grams. All right, so that's the molar mass that was given to us. We're going to use that in our last step, and we get 2.58 grams. All right, so that's going to be choice D in this multiple choice question. How many grams of sodium azide form? All right, so any questions on that? That was another example, just a little bit more complex because we have 3 reactants instead of 2. I don't think it'll get any worse than that, though. 3 reactants is likely the most that we'd ever bother you guys with. All right, but again, if it's anything more than 1, if we have amounts of 2 reactants or amounts of more than 2 reactants, the first step will always have to be to identify the limiting reactant to know which of those we're going to use to do the stoichiometry calculations. All right, last questions on that before our last stoichiometry topic, I think. At least in this chapter. I shouldn't say we're just not going to go forever. All right, the last thing we want to talk about is what's called percent yield. And this is more of an experimental factor that sometimes comes into play when you're doing chemical reactions in a laboratory. So, again, I sadly or ashamedly admit that I don't really know what goes on in the chemistry labs here very much in the lab portion of this course, which I should fix at some point. So I don't know if you guys have done a chemical reaction in the lab yet, but if you do, and when you do, you will have to likely calculate the percent yield of your reaction. So it's an experimental quantity that basically compares how much product you actually make in the lab compared to how much you should be able to make based on the amounts of reactants you use. So there's 2 things that go into this. There's theoretical yield and actual yield. So theoretical yield is the maximum amount of a product that can form. Or that can be attained, I guess is a better way to put it. If all of the limiting reactant is consumed. So in a typical problem that involves trying to find percent yield or something related to that, typically the theoretical yield is going to be calculated by you. That's what you use stoichiometry to figure out. So when you calculate, a limiting reactant, figure out what the limiting reactant is, and then use that to calculate how much product can form, that amount that you obtain from the stoichiometry calculations is going to be the theoretical yield. That's the most amount of that product that you can actually get. The actual yield is an experimental quantity, and so in many situations this will be given to you in the problem because we can't actually do experiments in CASA, and so it's going to be a problem amount that's given to you, and it's the amount of product that is obtained experimentally. So you go in the lab, you run the chemical reaction, you collect the product, you measure how much you get, and this is what is your actual yield. Usually expressed in mass amounts, although you could also convert it to moles or other quantities if you need to. But it's the actual amount of product you get experimentally. And there's no way to calculate this number. I mean, I suppose if we give you everything else you can calculate, but it's not a calculated quantity, it's an experimental quantity, okay? Now, why is it not often equal to the theoretical yield? So why do we not usually get as much product as we think we're going to get? There's a few reasons for that. So one is what's called experimental losses. So, you're doing the chemical reaction in the lab, and sometimes unavoidably some amount of your product is going to stick to the flask that you did the reaction in, or you collect it on a filter and some amount of the product is going to get lodged in the filter and not able to be recovered, stuff like that. Or if you just have ham hands and you drop some of the product, that's going to be an experimental loss also. So those are all the different ways that you can just have some of your product not get collected 100%. Even if it forms, it's just not physically collected. Sometimes you have what are called side reactions. We're not going to really talk about these in great detail, but this is a situation where either two or more of your reactants or your reactants and your product, they can react with each other in some other way that you don't want to have happen. So it's not that the chemical equation you write out isn't the only thing that's happening. There's other processes, other chemical reactions happening at the same time. They form different products, and that means the product that you're trying to actually isolate to prepare in the lab is going to be collected in a less amount. Or sometimes, as you'll learn more about in chemistry 2, you have reactions that don't go to completion. So in other words, they don't go all the way 100% to product. You have some reactants that just sit around and don't react with each other. That's a situation called equilibrium. Sometimes it's just a matter of not waiting long enough. So in some cases, if you just let the reaction go for longer, there is a time component to this. It'll go to completion and you'll get a higher yield. But sometimes it stops at a certain point. That's called equilibrium. That's something that is going to be covered ad nauseum in chemistry 2 if you guys end up taking that course, 1332 as it is here. But at any rate, once you know your actual yield and your theoretical yield, typically actual yield being determined in the lab or given to you in the problem in our case, and the theoretical yield, which you usually would calculate from stoichiometry, those two as a ratio and then multiply by 100 gives you what's called a percent yield. So it's actual over theoretical times 100. Anytime you have a percent, you should know that you're multiplying by 100. And this percent yield should always be less than or equal to 100. If you go into a lab and get greater than 100% yield, you might be proud of yourself, but it also means you mess something up, so you can't get more than 100% yield. It's physically impossible based on the law of conservation of mass and other things. All right, so your percent yield that you calculate should be less than 100, or at best equal to 100, okay? So that's one last thing we're going to have to do in some cases. So to put it all together, let's do a relatively involved stoichiometry problem that goes through all the steps that we learned today. So this is going to recap just about everything we talked about today. So we have WCl6, which is this sort of grayish-black soot-looking powder there. It can be prepared very simply by just taking tungsten as a metal, W, and chlorine gas, which has a formula Cl2. And so let's say someone goes into the lab and combines 5 grams of tungsten and 6.75 grams of chlorine gas. So those are the two amounts of reactants. We have amounts for both reactants, so we should immediately be thinking limiting reactant is going to be part of this. And at the end of the reaction, we obtain 5.92 grams of WCl6. That's going to be our actual yield, the amount of product that we actually got in the lab experimentally. What is the percent yield for this reaction? Okay? So just like before, our first step is going to be to write a balanced chemical equation. We don't have that here, so it's going to be W plus Cl2 making WCl6, a relatively easy equation to balance because all we need, we have 6 chlorines on the right, so we just need a coefficient of 3 to make 6 chlorines on the left, and that's all we need. So one coefficient to balance this equation. So not a terribly difficult one to do, but that's going to be our starting point. We have amounts for both reactants, so as I said, we're going to figure out limiting reactants. So we're going to do, our first step is going to be to calculate stoichiometric ratios. So we find the moles of tungsten. We have 5 grams of it. We convert to moles using its atomic mass, which we gave you here is 183.84. You could also have gotten that number from the periodic table. I just want to save a little bit of time by having the number available. And that gives us 0.0272 moles of tungsten. And then the stoichiometric ratio is just that number divided by the coefficient. The coefficient for tungsten is 1, so the number is the same, just 0.0272. All right, so that's our stoichiometric ratio for tungsten. We do the same thing for the other reactant, which is chlorine, Cl2. So for Cl2, we have 6.75 grams. We convert to moles using the molar mass of chlorine gas, which is given here as 70.9. And we get 0.0952 moles of Cl2. And the stoichiometric ratio is that number divided by the coefficient, which for Cl2 is a 3. We have 0.0317. So of these two numbers, 0.0272, 0.0317, the number for tungsten is smaller, so that's going to be our limiting reactant. Okay? So that's our first step. We have to know what the limiting reactant is to be able to do anything else that we're asked to do. So we've identified that it's tungsten W. And then once you know what the limiting reactant is, we can then calculate the theoretical yield. All right, so we have the next step is going to be we have our balanced chemical equation that we found. We know that tungsten is our limiting reactant W, so we're going to calculate the amount of tungsten hexachloride, WCl6, that can actually be formed in this chemical reaction. So this is going to be our theoretical yield. We have 0.0272 moles of tungsten. We calculated that in the previous step. And we're going to calculate how much WCl6 would form if all 0.0272 reacted perfectly. So we have mole ratios now. To get moles of product, we use the mole ratios. 1 mole of WCl6 is going to form for every 1 mole of W, so it's just a 1-to-1 ratio. And then we're going to use the molar mass for WCl6, which is 396.54, to calculate the mass of WCl6. We could also do percent yield calculations in moles, but since we're given the grams of product that form or that we collect, we're going to use the theoretical mass as well as a more direct way to do this. That's also WCl6. I should run out of room there. So 396.54 grams of tungsten hexachloride, or tungsten 6 chloride, I guess is a better way to say it, per mole of tungsten 6 chloride. And that means we calculate that we would get 10.8 grams of WCl6. And this calculated amount that we got from taking the limiting reactant and figuring out how much product forms from that, that's going to be what's our theoretical yield. Okay? All right, so that's our theoretical yield. That's the amount of product that actually could be formed if all of our limiting reactant was consumed. And then the last step, so those 2 steps we've already done before, the last step, which is the new one, is just to calculate percent yield, which, as we recently defined, is going to be the actual divided by the theoretical. Multiplied by 100. Okay? So in this problem, we're told that 5.92 grams of WCl6 was obtained. That's our actual yield. So whoever did this reaction in the lab got 5.92 grams. And then the amount that we calculated as our theoretical yield in the previous step was 10.8. That's the amount that would form if everything went perfect. Multiply by 100 to get it to a percent, and what we get is 54.8%. Okay? So whoever did this reaction got 54.8% yield, meaning that was 54.8% of the maximum amount of product that could be obtained. That's what they actually got. They might be thinking, oh, what a loser, they only got 55%. It really depends on the context whether that's bad or not. I mean, every chemical reaction is different, so when you're doing these things in a lab, sometimes 55% is a great day. Sometimes there is room for improvement. It really depends on the specific reaction you're studying. Okay, that's what we get for this problem here. So as far as I know, that takes us to the end of chapter 5. So any last questions on stoichiometry before we move on to the next chapter? All right. So what we're going to do in chapter 6 is we're going to talk. It's still a lot of stoichiometry, still a lot of chemical reactions, but we're going to specifically talk about chemical reactions that happen in solution. So when you have reactants that are dissolved primarily in water, for the types that we're going to talk about, and the different types of chemical reactions that can occur in some aspects of their stoichiometry that are a little bit different than what we've been talking about so far. But a lot of the concepts are very much the same, just extensions of what we've already been doing. Now to get into this, though, before we really get into the stoichiometry part, which is going to come much later, we're going to first define some different things about aqueous solutions. We're going to characterize a few types of reactions that happen in aqueous solutions. So it's going to be a lot of conceptual things to start with, and then we're going to get into the stoichiometry stuff at the very end after we put all that together. So first, some initial definitions that we're going to talk about. We haven't talked really about solutions yet. We've only talked about pure substances primarily so far. So a solution is a mixture of 2 or more substances. It's homogeneous. So these are some terms that we have touched on briefly before and are probably ones that you've seen in previous courses, whether they be chemistry or otherwise. But a solution is a homogeneous mixture of 2 or more substances. Now, homogeneous means that it's a single phase. So we can't tell that we can't easily tell that we have two or more substances. We can't look at a solution and say, oh yeah, that's two things mixed together. It looks like one thing. It looks like one substance, but it's actually two or more mixed together. And it usually involves a liquid. So the types of solutions we're going to primarily deal with, especially in this chapter, are going to be liquid solutions. They have a liquid that dissolves some other substances that are going to be contained in that liquid. So it's usually involving a liquid, but it doesn't have to be. The definition is more general than that. So examples of solutions would be things like salt water. So if you dissolve salt in water, or if you collect seawater, I suppose, that would be a solution also that has things dissolved in water. You look at it, you can't easily tell that there's that salt dissolved in the water. It looks just like water if you just look at it, but there are two substances there that are together in a solution. Most beverages that you drink, whether they be the ones that you have in front of you now or ones that you might have during spring break, those, not that I'm suggesting anything, those are mostly solutions. If they're, things like, okay, let's be clean here. Things like juice. Most juices are solutions. They're colored liquids. They don't look like they're more than one thing in there, but there's a lot of things dissolved in that liquid, which is, again, mostly water. But beyond, liquid solutions, we also have air as a solution. So air is a mixture of all kinds of gases. You can't tell by looking at it that there's a lot of different things there, but it's 78% oxygen, 78% nitrogen, 21% oxygen, and 1% of a bunch of other things like carbon dioxide, argon, very small components of many other gases. But there's a lot of things mixed together in air that's considered a gas solution. And then gasoline would also be another solution. So it's a mixture. There's no water in gasoline, or very little water in gasoline, but it's a mixture of all different, primarily hydrocarbon substances. So that would be an example of another solution. So these are just examples, and that's what we mean by solution. Now, what we're going to talk about in this course is mostly aqueous solutions, and in this case, we have two components that are very easy to identify. You have solute and solvent. So the solute is conventionally what you would refer to as the minor component. And it is what's dissolved. It's the substance that is dissolved in the liquid. Okay? So if you make salt water, salt would be the solute. It's what you're dissolving into the water. And then the solvent is the major component, which, typically speaking, is the liquid that is used to dissolve the solute. So the major component of a solution is the solvent. Or you can think of it as the substance that does the dissolving. In our context, this is primarily a liquid, usually water, for the types of chemical reactions we're going to talk about. So it's usually, in our case, it's going to be obvious. In some situations, if you have two liquids mixed together in similar amounts, or gases mixed together in similar amounts, it's not really unambiguous which one's solute and which one's solvent. It's kind of arbitrary in those cases. But for the types that we're going to talk about, you have typically water as your solvent, and you're going to have some things dissolved in water, usually ionic compounds or acids or things of that sort. That would be your solute. Okay, so those are the two components. And if we have a solution in water, where water is a solvent, we call that an aqueous solution. Okay, so that term aqueous means dissolved in water. Okay, so there are a lot of other liquids that you could use as solvents, and in chemistry labs especially, we use those a lot besides water. But in this case, we're talking about a solution in water. It's called aqueous. Okay. Now, one thing we also want to review before we go forward is, we've kind of established with this that water can dissolve a lot of different substances. We'll see that throughout this chapter. So why is water good at dissolving things? And that's because of its polarity, this is sort of a review of things we talked about a few chapters ago in chapter 3 and 4. So why is water polar? So here's some, this one here is H2. This one is H2O, showing how it's polar. And there's a few reasons for that we've already covered in this course. So one is that we have different electronegativities. So oxygen is more electronegative than hydrogen, which leads to a polarization of the bond and unequal distribution of electron density. In addition to the individual bonds being polar, as we said in chapter 4, the shape of the molecule matters as well. Water, as we should know by now, has a bent shape. So we have these two bond dipoles that don't cancel each other out completely because they're in a bent arrangement, not linear to each other. And so what that leads to then is water has not fully negative, but partially negative and partially positive poles associated with it, where it has a region of negative electron density, a region of positive charge. And that is what's responsible for its ability to dissolve a lot of compounds. So there's some pictures of this here, but essentially, as we talked about in many cases, you have two polar bonds, and that leads to, in water, delta minus near the oxygen, delta plus near the water, or near the hydrogen. So you have two poles that are associated with this. And because you have this imbalance of charge and this partial negative and partial positive, water is going to be attracted to many solutes, especially if the solute is also either a polar compound that has its own partial positive and partial negative regions, or if the solute is an ionic compound and has actual positive and negative ions, the poles in water are going to be attracted to those solutes and assist in the dissolving process. Okay, so let's take a look at how that works. I have a couple of videos here that are going to show us, or one video specifically that's going to show us what happens when something dissolves in water. All right, so here we go. I don't know if I can enlarge. I guess I can full screen that, but it doesn't change much. All right, so this is supposed to be a simulation, but it's actually just a video. It looks like a simulation, but it's actually a video. I can't find the original source of this, so we're just going to watch somebody else have fun with the simulation. All right, so what we're going to show here is we're going to show dissolving two substances in water. The first one is going to be NaCl, which we should recognize as an ionic compound. So you can put salt into the water. Now let's look at a molecular level of what's happening. So we know that the salt will dissolve and form a nice homogeneous mixture. We can't even tell it's there anymore. But what's going on at the atomic and molecular level? So eventually whoever made this video is going to, in a painstakingly slow way, click the zoom button. There we go. All right, so let's see. We have positive and negative ions that make up the sodium chloride. The sodium is positive, chloride is negative. And the water is going to come over and it's going to separate those ions from each other. So if we do a quick snapshot of this, we can see, once I get enough, or, come on. All right, come on, pause. There we go. So we see in this one here, we have this negatively charged chloride ion. And remember that the hydrogen atoms on water have a partial positive, and those partial positive charges on the hydrogen atoms are going to surround the negative charge on the chloride. So the opposite charges sort of attract to each other, and the water molecules are going to pull the chloride ion away and separate it into the solution. And if you watch sodium, here the opposite happens. The oxygen atoms from water, which are partially negative, surround the sodium atom, and the opposite charges again attract each other. So that's what happens. All these little salt crystals, we're going to learn more about the structure of salts later on, but they're going to take the individual ions and pull them off into solution, and they're going to make new attractions with the water. Now, if we do a covalent compound, so methanol, which is an alcohol, not one that you should drink though, is a liquid, and that can also dissolve in water. It's very poisonous. I'm actually being serious about that. So it dissolves in water also. Now let's see what happens when that type of substance dissolves. So it's a polar covalent compound. It also has oxygen and hydrogen, not too different than water really, just a few other atoms in there. So it has its own partial positive and partial negative charges that are going to then attract to those same charges or the opposite charges in water. So initially when you have liquid methanol, it has its own sort of dipole-dipole type interactions. And then when you put it in water, the water molecules are going to come, they're going to surround the other solute molecules eventually and start pulling them apart from each other, making their own new attractions between the dipoles. Again, oppositely charged dipoles attracting each other. So these are going to go off into solution and separate and be surrounded by water molecules now, and that's what the process of dissolving looks like. But you'll notice a key difference here. We're not actually breaking the molecules apart. The molecules are still intact. So in a covalent compound, you don't form ions. You don't break anything apart. You don't break any bonds. You don't make ions. You just surround those molecules and pull them into solution. So there's a key difference there between ionic and covalent compounds. All right, so to quickly summarize what we saw in those videos, I have the link here, so you should be able. I can only get this video to work in Google Chrome for what it's worth. I don't know if that's a universal limitation or just on my tablet, but anyway, you should be able to see this at home if you want to watch it again. But the key point here is that in ionic compounds, The individual ions separate in solution, so you get charged ions separating into solution. Whereas for covalent compounds, the example we showed there was methanol, which is a covalent compound. When you dissolve a covalent compound in water, there's no breaking of any bonds. So the molecules stay intact, but you still have a process of dissolving that involves separating those molecules from each other. The water molecules still surround the other molecules, but they don't actually break them apart like they would in an ionic compound. So in solutions of ionic compounds, you have charged ions actually present in solution. Covalent compounds, you don't have that situation. So because of that difference between ionic and covalent compounds dissolving in water, they also have then some different properties associated with them when you make solutions. So the next video we have here, this guy loves himself a lot, as you'll see. This is only the beginning of it. So in these types of solutions, they have different properties. So what he's going to do is he's going to make two different solutions, actually a bunch of different solutions. Some of them are ionic compounds, some of them are covalent compounds, and he's going to test whether or not they conduct electricity by using this light bulb. So first he's going to start with tap water. We should recognize that tap water is not pure, so it does conduct electricity a little bit, as we saw there. If we do pure water, distilled water, there's no conductivity. So pure water does not conduct electricity by itself. This solution has sodium chloride in it, and you can see that it conducts electricity very well. Hydrochloric acid, a strong acid, conducts electricity very well. Sodium hydroxide, another ionic compound, conducts electricity very well. So all these ionic compounds and strong acids, when they dissolve. If we go to sugar, though, which is a covalent compound, we see that there is no solution conductivity. And then vinegar, which is a weak acid, we can see that it lights up, but not nearly as bright as before, or not too different anyway. All right, so let's do one more. This is another covalent compound, very similar to methanol. This is ethanol, just a little bit different. This one you could drink if you wanted to. Still not great for you. Not a good idea. This guy has no regard for personal safety. Now, this is an ionic compound that doesn't dissolve in water. So it's an ionic compound, but it doesn't actually dissolve. And you can see that it doesn't conduct electricity. So the only time that ionic compounds conduct electricity is when they actually dissolve in the water. Okay, so that was a series of experiments showing the difference in conductivity. I don't know why I guess that guy was pretty embarrassing, which is why they suggested the most embarrassing moments in sports after that. But anyway, we saw some key differences there. So when you have ionic compounds in solution, you have free ions floating around, so they are able to conduct electrons, conduct electricity, and the light bulb lit up in those cases. So ionic compounds in solution conduct electricity. They don't conduct electricity by themselves. They have to be dissolved for that to happen. You have to have the free positive and negatively charged ions separated from each other for that electricity to be conducted. And then also we saw that covalent compounds is the opposite. Now, any solution that conducts electricity, what we call that is an electrolyte solution. So you've probably heard the term electrolyte before in the context of health and fitness. And what its precise definition is from a chemistry standpoint is it's a substance that, when dissolved in water, will conduct electricity. So any of those substances that conduct electricity when they're dissolved are considered electrolytes. Okay, so any solution that conducts electricity is called an electrolyte solution. Now, within this electrolyte solutions, we have two subcategories. So we have strong and weak electrolytes, and we also have substances that are non-electrolytes. So strong electrolytes, there's two categories of compounds that are classified as strong electrolytes. In the context of that video, those are the ones that conduct electricity really well. And these would be anything that's a soluble ionic compound. So next time we're going to learn how to predict which ionic compounds are and are not soluble, which ones can and cannot dissolve. But any ionic compound that dissolves in water will give a strong electrolyte solution. Now, the other type of compound that dissolves in water to give a strong electrolyte, we saw one example of it in the video, are strong acids. So we're going to talk more about the behavior of acids in this chapter as well, so I'm not going to go through all those details now. But when strong acids dissolve in water, they also separate into ions. And so you get that same type of behavior where you have ions in solution that are able to conduct charge, conduct electricity. We'll talk about strong acids later on, but the examples that are most common in this course are going to be things like HCl, which he looked at, nitric acid, HNO3, sulfuric acid, perchloric acid. So those are some of the most common strong acids. We'll talk about that later on in more detail. And the key point is that when these substances dissolve in water, they conduct electricity really well. Now, there's not really a quantitative distinction between strong electrolytes and weak electrolytes, but weak electrolytes would be compounds that partially break down into ions and only weakly conduct electricity. We're not going to talk a lot about weak electrolytes in this course because there's only one class of compounds that really falls into this category, and we're not going to talk about those types of compounds in very much detail. You'll get a lot of that in Chem 1332 as well. But when these compounds dissolve in water, they partially break down into ions, so there are some ions formed, but most of the molecules remain intact and behave more like covalent compounds. So they're kind of in between case, and they weakly conduct electricity. So the only category of compounds that really falls into this would be weak acids, which is basically all other acids besides the few that I listed above we would assume are weak acids. Weak bases would also fall into this category. The only example of a weak base that we'll see in this course is NH3 ammonia. So you're going to get a lot more details about weak acids and weak bases in Chem 1332. For our purposes, we just need to know that those types of substances, when they dissolve in water, are classified as weak electrolytes. They do form some ions, but most of the molecules remain intact, and you only get relatively weak conductivity because you don't have a lot of ions in solution to conduct electricity. A key principle here that I didn't really enumerate yet, but should be hopefully fairly intuitive, is that the more ions you have in solution, the more electricity you can conduct. So even if you're taking the same solution like salt water, if it has a little bit of salt in it, it's not going to conduct a lot of electricity, but if you put a lot of salt in it, you'll get a lot more conductivity and a lot brighter light bulb in that experiment that guy did before. The last category of substances are non-electrolytes. So when these dissolve in water, they have no electroconductivity. And the categories of compounds that would be considered non-electrolytes are covalent compounds, specifically ones that are not acids or bases. And the classic examples that we'll see in this course all the time are alcohols. So these are a lot like water, but they just have some extra carbons in there. So alcohols, things like CH3OH, CH3CH2OH, methanol, ethanol, the two that we've seen already today. These are kind of the classic examples. Sugar would be another one. I guess I can write that down here. It's a pretty common example. Most sugars are polar covalent compounds. So table sugar, which is sucrose, or other types of sugars, they dissolve in water, but they're covalent compounds, and they don't conduct electricity when they're dissolved because they stay intact as molecules. All right, so that gets out some of the basic definitions for Chapter 6. What we're going to start with next time, the last time before spring break, is discussing different types of chemical reactions that happen when aqueous reactants combine with each other.